Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest is Amar Vutha. He's a Canadian research chair in precision atomic and molecular physics. And he also deals with machine learning and, a lot of interesting questions, things that most people, I'm sure, don't think about. So, Amar, thanks for coming. How you doing?
I'm doing well. Thanks for having me. It's been a pleasure to chat with you.
Oh, good. So what, in your mind, what's some of the most interesting stuff that you're working on right
now? Of course, everything I do is awesome and interesting, right? But
yes.
I'll maybe say that, there are questions which I wish I knew how to answer, and I don't know how to answer them yet. And so to me, those are the ones which are the most interesting, because those are the ones which I feel like if I was smart enough to figure out how to work on those, I would be working on.
Well, what's something that you have figured out that's really surprising to maybe the scientific community outside of your direct work that you think is really important?
Well, again, I should preface this by saying that the things I work on are measuring properties of atoms and molecules. And so these are, in some sense, things we do because we want to understand more about how the universe works, unravel some of the mysteries about the universe. But none of these are going to be important or useful to anyone in the broader sense, right? They're not going to help find cures or lead to faster washing machines or anything. So it's mostly things that we do to try to understand why the laws of physics or why nature works the way it does.
Well, let me ask you a question here. So, if I think about different atoms or even different molecules, as far as I know, the only difference is the number of electrons, neutrons, and protons. So why do they have these emergent properties? Like, why do different elements have these very different emergent properties? And why do molecules have all these amazing different properties when fundamentally they don't appear to be very different from one another?
Yeah, that's a great question. So the best way to think about this is that it's like a bunch of houses which are all built out of the same things, like bricks and mortar. But depending on how they're put together, they can look very different and, of course, have very different properties. And so that's the way in which, even though the building blocks of every atom is electrons and protons and neutrons, when you start stacking more and more electrons into atoms or molecules, for example, these electrons have the property that they don't like each other, so they try to avoid each other in a very colloquial sense. And so because of that, the atoms sort of have to change their structure as more and more electrons get added. And this is what people call the shell model of electrons. And this happens in nuclei as well. And so because of this, as you add more and more electrons, the chemical properties and the physical properties of all these atoms change a lot. And so going from something like hydrogen, which only has one electron, to, let's say, something crazy like mercury, which has lots and lots of electrons, it has 80 electrons. The difference in the chemical properties that you're used to, that you know from chemistry, those are all because of exactly this fact that with lots of electrons, the interactions between them make the atoms have lots of new properties.
Yeah, it seems like most of chemistry is, the currency of chemistry is electrons, a lot of it. It's the trading of electrons or the usage of electrons and the different energy levels that they contain seems to underlie a lot of chemistry. I don't know if that's right, but it just seems like it. Is that the case?
No, that's absolutely right. A lot of chemical reactions have to do with different atoms trading electrons, right? Swapping electrons from one to the other. And so, electrons are the glue that binds the atoms together to make molecules.
Well, what does that tell you? It seems like, I don't know, it's just weird that, that molecules have all these properties. I mean, even when we eat food, what are we consuming? We're consuming various levels. Like if you look at the electron transport chain in in us, let's say, we're eating energy levels. We're taking in energy essentially, right? It's weird.
Yeah, well, we're eating electrons. We're breaking apart different molecules and making new kinds of molecules. And depending on whether we need to spend energy to break those molecules, or whether we get energy by breaking those molecules. That's what ends up defining whether we get something from them, or whether we have to spend energy to use them. So it's all a big swirl of energy and electrons back and forth. That sort of stuff, though, is have to admit it is a little far removed from the sort of things I work with, in the sense that most of the experiments that we try to do, we try to avoid any kind of massive interactions between lots of atoms or molecules. In other words, we want to understand properties of individual atoms and individual molecules as closely as possible without having them be affected by what they might do if they bump into other atoms, or what they might do if they trade electrons with other molecules.
So what are you looking at trying to understand? Well, give me some specifics on what you've been working on.
So maybe let me step back a little bit and give you my personal take on what I think are three of the most important unsolved problems in physics. And again, this is my personal take. I'm sure there'll be others who think other problems are more important, so that's all good. But at least according to me, here is what I think are the three most important problems. And one way to organize these problems is to think of them as how much stuff there is in the universe. Okay? And so, for example, if you think about the universe as a pie chart, a big slice of pizza, so most of the universe is something called dark energy. About 70% is dark energy. Now, we don't know what dark energy is. No one knows what dark energy is. All we know is that it's some kind of energy. And wouldn't it be nice if we could figure out more about this stuff, because it seems to, really be a huge part of our universe. And so that's a question which lots of people are sort of trying to rack their brains and try to figure out. But we don't really have any good approaches to figuring this out yet. So that to me is the single most important problem. I wish I was doing something more directly related to it, but that's one of the problems which I don't think I'm, so far at least, have been smart enough to figure out a good way to make progress on. The second most important problem, in my opinion, is the remaining part of the universe. So off that remaining 30%, something like 25% is something called dark matter. And again, we don't know what the heck this stuff is. It's all we know is that it behaves like matter, right? It pulls on other things because of its mass. And it's important in things like the formation of galaxies, but we've only gotten information about dark matter from what it does in astrophysics. We've never been able to make dark matter in the lab. We've never been able to study its properties in the lab in a controlled environment. And so that's not great either. So again, wouldn't it be nice if we had some way to figure out what dark matter is?
Quick question here.
Yeah, sure, go ahead.
Does dark matter, is it around us right now, for instance, like in a lab experiment? Can it be observed, or the action of it be observed, the inference be made locally, or is it only far away?
Well, we'd like to detect something about it locally. But the expectation is that, yes, right now, you and I are just being bombarded by huge amounts of dark matter particles. They just don't interact with anything that we know about. They're supposed to be interacting so weakly with all of the stuff inside us that it's really hard to do any kind of experiments. In other words, if you were standing in a swarm of locusts, you would know it, right? They'd smash into you. But we're sitting in a swarm of dark matter particles, and they're just going right through us. And that's the problem with them. They interact so weakly that it's hard to directly detect if they're around. It's hard to confine them and doing things of that sort. So the best we can do is try to build more and more and more sensitive devices to try to pick these things out, to try to see if they might give us clicks if they hit something in our experiment. And so that's the sort of place where, for example, atoms and molecules can be helpful, because we understand the structure of atoms and the structure of molecules so well that it's easy to look for very, very, very small deviations from what we know should be the properties of these things. And so that's the way in which atoms and molecules are useful. What you do, at least the cartoon version, is you take your atom that you understand really well, and then you hold it in this stream of dark matter particles, or you assume that it's being hit by dark matter particles, and then you ask if the stuff inside the atom, the protons and the neutrons and the electrons, were somehow being affected by this dark matter particle, what would be different about the properties of this atom? Would it have, for example, a different mass? Would it have a different magnetic moment? And so you sort of try to study these kinds of properties and use them as a way to sense if there might be some new crazy particle out there. Other people, of course, are doing this at places like the Large Hadron Collider by smashing stuff together and trying to see if dark matter particles might pop out. So there are lots of ways of looking for these kinds of things. But certainly atoms and molecules gave us one possible way to find them.
If you create a vacuum space, in a chamber, is there the same amount of dark matter in that chamber, do you think, before and after the vacuum's created?
Yeah, because the way you make a vacuum is you first of all make a sealed box, right? And you make a metal box or something, and then you remove all of the gas inside it using a pump. But dark matter is so weakly interacting that it would just go through the metal box and it would not really get affected by anything else. So even if you made a really good vacuum system, you would still expect to find a lot of dark matter inside it.
Right, but would you find, the percentage of total constituency inside that box, would it be more dark matter by percentage now?
That's right.
Because you've removed everything else.
Yeah, for sure.
So maybe you could figure out something if you made, such a high vacuum, such a complete vacuum that there was, just about nothing there. Maybe you would see, certain properties of the vacuum that came from dark matter, or see it there somehow, or observe it.
That's a great idea. And, since people have been thinking about similar sorts of things where, let's say you made a really good vacuum and had a few atoms sitting around inside it. Every once in a while, if a dark matter particle bumped into them, it would sort of knock them around. And then could you look for, because you can, look at individual atoms these days with the technology that's available, and you can really study individual atom properties. Could you try to catch one of these atoms getting knocked by a particle of dark matter? The problem with all these kinds of things usually is the statistics of it. So what I mean by that is, dark matter is so weakly interacting that to have any hope of having dark matter be, give you a click when it hits something inside your experiment, you want your experiment to have lots of stuff, because the per atom probability that any dark matter particle will bump into it is so low and so weak that just to get the numbers up, you tend to want lots of stuff inside. So one of the leading approaches to look for dark matter is at an experiment in Japan where they have huge tanks of really pure water. And these tanks of water are surrounded by extremely sensitive cameras looking for little flashes of light that will come off if dark matter hit one of these water molecules or water nuclei and gave off a little flash of light.
What about neutrinos? I thought systems like that also detect neutrinos coming in.
Exactly, yeah. So in fact, this experiment that I mentioned in Japan, that is a neutrino detector. And similar kinds of techniques that you would use to look for neutrinos are being used to look for dark matter. Because you're right, neutrinos are very similar. They also interact really weakly. And so you could just use similar ideas. And so that's what a lot of approaches doing around the world. Lots of experiments are really looking for them using the techniques that they developed to look for, to basically make very high precision neutrino measurements. So far, nothing, right? And so that's the challenge here. Are we even looking in the right place? Is there something fundamental about these things that we're missing, right? And that's always the worry. Is, you're looking under the lamppost just because you know where to look. Doesn't mean that that's where you lost your keys.
Do you think that science understands the structure of atoms as completely as it needs to? I mean, I know it seems to me there's a, because of the Heisenberg uncertainty, there's a curtain through which we can never go or see through. But I mean, how far have we come in our understanding just of, let's say, the structure of the given atom? Now, I know about the electron cloud model, but I've been hearing that the nucleus itself has a structure, larger atoms. And I mean, what's the latest and greatest in terms of atomic structure that's new and revealing?
Well, so the structure of atoms is quite well understood in the sense that we know exactly what laws of physics they obey. Now, if I give you an atom like mercury, for example, which has lots of electrons, actually calculating what that structure is with pen and paper or even a powerful computer is pretty hard, it turns out. And the reason it's hard is, again, quantum mechanics. And it's not even really Heisenberg's uncertainty principle. It's the fact that in quantum mechanics, there's a lot of information involved, even when you deal with 80 electrons. And keeping track of all that information, keeping track of all the wave functions of all the electrons and what they might be doing, what kind of superpositions they're in, all that sort of information is really complicated to keep track of. And so any calculations we do tend to be approximations. Now, these approximations are pretty good in the sense that they're good enough for us to start calculating some properties at the level of, let's say, a part per thousand even. Right? So for a mercury atom, just from first principles, just using pen and paper and computers, you can calculate the properties of mercury to the 0.1% level. But experiments can, of course, do way better than that. We have experiments these days that can measure the properties of atoms to 18 decimal places. And so the calculations can't quite compete. But in the sense that the sense in which we understand their properties well is not that we can actually tell you exactly what these properties are just by pure thought, but it's more that we understand what the laws of physics are that they obey. And so we know what the patterns are that they should display. In other words, we know something about what sort of symmetries they should have. We know that if you pack 80 electrons into an atom, that atom is going to be very, very, very spherical. It's not going to have an elliptical shape. It's not going to look like a football, right? So those sorts of properties, things like that, we know extremely well. But actually, like I said again, there are some properties which we don't really know too well.
Yeah, I spoke to a scientist named Preston McDougall, and he said that molecules, at least, and atoms, they do seem to have an electrical shape that's created by the overlapping of their electrons and different energy levels. And there seems to be pits and bumps and holes and things like that. So that tells me, I wonder if there's like a braille language of chemistry that allows bonding and disallows bonding, and if that's missing in current in current chemistry and understanding of atoms. Like for instance, he looked at noble gases, and they appear to be very perfectly spherical, in terms of their the shape of the electric field of the electrons. Maybe that's a clue as to why they don't bond well. So have you looked at that? Is that part of the understanding?
So it's not just the shape of them. It's also, of course, like we said, how willing they are to trade electrons and give off electrons and catch them and so on. So let me give you an example. So a system is floating, and same for noble gas atoms. But even though sodium atoms are quite spherical, they react like crazy, right? They make salt, they make all kinds of other chemicals. So sodium is a very reactive element. And so, so it's not just the shape that's involved in reactivity. It's also something to do with how readily they lose their electrons, how readily they gain electrons. And so, so that's the, those are the details of chemistry. But it's not quite as simple as just the shape.
Oh, I didn't think it was, but so in your mind, what does govern why a sodium would be very reactive and another element wouldn't be very reactive? What is actually the difference besides just, it has an unfilled, a valence shell of electrons? I mean, that doesn't really say anything. What is the real reason you think why that happens?
Well, so it's to do with the following thing. So let's say you take a sodium atom and a chlorine atom, and you hold them 2 miles apart. At that distance, they don't really know about each other's existence. Or to be more specific, what I mean by that is the electrons in the sodium don't really overlap with the electrons in the chlorine. But now you bring these atoms close together. You bring them close enough that the electrons from one of the atoms has enough probability of appearing at the location of the other atom. And because electrons are waves, they can be diffused. They don't have to be in one single place. So the idea is that you have electrons which can be on one of the atoms or on the other atom. And then at that point, it's a question of energetics, right? So you can say, hey, look, I have this system of electrons. Is it energetically favorable for all the electrons, or for, let's say, 11 electrons to live on sodium and then the remaining electrons to live on chlorine? Or is it more energetically favorable for one of the electrons that used to be on sodium to go and hang out on the chlorine? So energy comes in there as well. And so that's the answer to why molecules are stable. It's because energetically it's favorable for this whole collection of electrons and protons and neutrons to form a molecule when these atoms are a certain distance apart than for them to retain their independent atomic identity. Yeah,
it's just, I don't know, it's just weird. If you consider an electron that gives off a photon and let's say falls to a different energy level, what's different about that electron? It has less energy, but is there anything else different about it?
No, that's all it is. And I agree. It's totally crazy, right? Because it's not just that electron is not that different. That electron is no different from any other electron in the universe. Every electron in the universe, other than the details of exactly what energy it has really the exact same property. And that's pretty cool too. And in fact, that's one of the other ways in which you can use these kinds of things to test the laws of physics and look for crazy things like dark matter and dark energy, is by using the fact that, yeah, atoms and molecules are created equal in some sense, at least as far as we know. So if I look at, a sodium atom in my lab compared to a sodium atom on the far end of the Andromeda galaxy, they really have the exact same properties. And so knowing in other words, by making really precise measurements on sodium atoms in labs on Earth, or other kinds of atoms and molecules in labs on Earth, and by looking in space and seeing what these atoms and molecules behave like when they're close to black holes, when they're close to stars, when they're out in different parts of the galaxy where there's more dark matter, where there's less dark matter, you can actually use these as probes, even though you don't directly get to go out there. And so that's also kind of a cool thing you can do, just using the fact that, the laws of physics say that if you take 11 electrons and put them in around a system with 23 nucleons, you will get a sodium atom.
And you can see their signatures even from millions and billions of light years away, and know that they're out there.
We can see light. Exactly, yeah, and that's pretty cool, right?
Yeah, definitely.
They're like standard beacons almost. It's sort of like you look out and then that there's a thing out there whose properties you understand, and now you can see what the light from it looks like.
Have you ever, or have you known anyone to take a large atom, let's say a mercury atom, and just denude it of all its electrons, ionize the heck out of it so it has literally no electrons, and then look at its properties?
Oh, yeah. Yeah, I mean, if you take away all the electrons, you just get the nucleus. And sure, there are people who make beams of these things so that they can smash them into other things. So, for example, a lot of nuclear physics experiments will use lead atoms and strip all the electrons off, just get the lead nuclei. And now you can accelerate the lead nuclei because they're charged. So you can make them go at really high speeds and then smash them into other things. People use gold nuclei in the same way. And then there are also people who will do things like remove almost all the electrons. So now you have something that's like a charged atom, that's an ion, but it hasn't quite lost all the electrons. So you've taken something complicated, or used to be complicated, like lead with lots of electrons, and then you've left, let's say, 1 or 2 electrons around the lead nuclei. And because, again, you've reduced the number of electrons, the properties of these things, these highly charged ions, as they're called, can be quite cool. They can be quite interesting.
Oh, I guess, yeah, you could bring them to, a hydrogen-like state, and they just have 1 electron.
Yeah.
And so,
totally.
what are some of the interesting properties that has been seen by doing that?
So one interest in making these kinds of highly charged ions is to try to make really accurate atomic clocks. Okay, and so atomic clocks are basically, they use the fact that if you, for example, have a bunch of energy levels in an atom, and if you whack an atom, okay, quite simply speaking, if you hit an atom tends to sort of ring at its natural resonance frequency, sort of like a bell. You hit a bell, it rings at a few specific frequencies. And so with atoms, the specific frequencies that they ring at are optical frequencies. So they're equal to, for example, the frequencies of laser photons. And so an atomic clock is really very similar to the way you would, tune a musical instrument. So imagine you had a violin and you had to keep it in tune. Well, every once in a while, you'd compare it to a tuning fork, and then you would say, okay, I need to dial up the tension on some of the strings or dial it down. In very much the same way, an atomic clock uses lasers. And periodically what you do is you compare the laser against a tuning fork, in other words, an atom. And you use the atom sort of like you would use a tuning fork to check, okay, is my laser running higher in pitch than it should be or lower in pitch than it should be? And so that's the basic idea of an atomic clock. But the point is, an atomic clock is only ever as good as the atoms inside it. In other words, if your tuning fork itself is flaky, let's say you were a concert violinist, but you used a tuning fork that changed its length because of the temperature, that wasn't stable, then that wouldn't make for a very good quality tuning of your instrument. So in the same way, when you use atoms and atomic clocks, you want to find atoms which are not very responsive or which are not very affected by all of the noise and fluctuating quantities we have in the world around it. And so one example is, let's say, magnetic fields. Another example is heat. And so all these things sort of, make the properties of atoms change very slightly. And for an atomic clock, you want atoms whose properties don't really change very much at all. You want them to be rock solid. And so that's where some of these highly charged ions come in. Because they're so highly charged, what happens is that the electrons in these atoms hang out really close to the nucleus. Okay? And because they're so close to the nucleus, it's very hard for external stimuli or external causes like heat and magnetic fields and such to perturb the properties of these atoms. Okay? Whereas in regular atoms, like sodium, lead, or whatever, the electrons live a certain distance away from the nucleus, so it's easier at least for the electric and magnetic fields to sort of pull the electrons away and change the properties of the atom and so on. And so that's one of the reasons why people are interested in these highly charged ions, is because they're really like rocks. Right? They don't get affected by a lot of the things that affect most atomic clocks today. And so that's the hope. The practical problem, of course, is that they're harder to work with, they're harder to make, they're harder to keep in place while you make measurements on them and so on. But that's a challenge which people are actually working on in quite a few labs around the world.
I'm sure the highly charged ions are like crack fiends for electrons. They're desperate for them. They can ionize anything.
Yeah, and so one of the other things you need to watch out for is if you're doing a highly charged ion experiment, you got to make sure that you don't have too much other gas inside your vacuum apparatus where you're working with them. Because again, they're sort of like catnip, right? Because they're so highly charged, they in fact tend to attract other atoms close by, and then they steal electrons from other atoms and molecules. Okay, it's a bit of work to try to keep them isolated and also to manipulate them, to hold them in place. But like I said, these are techniques which are being developed, and people are getting better and better at them.
Has anyone been able to model a collision of two atoms, like picosecond by picosecond, and look at the shape of the electrons, the electron clouds, and how they deform, how something collides? Has that been done?
Yeah. And the thing they use for that is it's called a pulse laser. And so basically, you should think of that as sort of like a flash camera. And yeah, using pulse lasers, people have looked at what happens during molecular collisions. Some of the work I've done has involved not quite imaging molecules during collisions, but trying to understand what happens to, for example, the quantum information contained in these atoms when they collide. So there's a lot of interesting work that people around the world are doing on studying collision, studying the energetics, but also, as you say, things like what happens to the electrons by instant while they collide.
Well, anything interesting observed from that? Does it look, is the deformation interesting looking? I mean, are there new things revealed by it?
I would say yes and no. So it certainly is cool in the sense that we have all these neat techniques now. And so especially for complicated molecules, maybe like biomolecules, let's say you even want to understand what happens during photosynthesis. You want to understand why light allows certain electrons to come off certain molecules and make energy. And so if you want to understand that process, it's neat to be able to do sort of a really fast flash photograph of that entire process. And so that's the sort of thing you can do with pulse lasers. And so you certainly do learn quite a lot of interesting details of what the electrons are doing in this process. But at a sort of much more fundamental level, these are all, in some sense, consequences of quantum mechanics. Right? In that sense, there is no real new physics that's coming out of these things. There's certainly lots of interesting chemistry. And I want to stress this is not a value judgment or anything. It's just a sort of a useful way to separate what the sciences you're learning from these. But there's not really any new physics in the sense that we know what the underlying quantum mechanics is, and we know what the underlying physics is that's holding these atoms and making them do stuff. It's just that when you get to something complicated like a biomolecule, it's really, really hard to model exactly what's going to happen from first principles. Again, like I said, even an atom like mercury is pretty hard to understand. And so when you get to really complicated molecules, just keeping track of what the electrons are doing all the quantum mechanics of it, just becomes a very hard problem just in terms of the amount of information that you have to process. So that's where these kinds of experiments are cool, because you can learn things from that you wouldn't be able to calculate very easily. But I don't think there's any doubt that the fundamental mechanisms holding these together are these well understood quantum mechanics.
So what else are you looking at that's like really interesting to you? I mean, whether you're looking at it or other scientists, but I mean, what are some things that you're really intensely curious about figuring out?
All right, so here's the third one on my list of questions, and the third one is a really weird one. So, like I said, 70% of the universe is dark energy, 25% is dark matter. We don't know what they are. Wouldn't it be great to figure out what they are? Cool. Now, everything we see around us, like all of the stuff, right? And I really mean everything, like including all the galaxies. If you look at all these photos from the Hubble Space Telescope, and there's thousands of galaxies on it, every single one of those. You add all that up, that's 5%-ish of the universe. It's around 5%. And that we think we understand fairly well, right? Those are the laws of physics we understand. But the kicker is we actually don't quite understand even that 5%. And the reason is that even though we see all the stuff, we don't see any antimatter naturally in the universe. Okay? And so what do I mean by that? So we know that way back in the Big Bang, everything was energy. And all the matter sort of formed from that energy. And when you form matter out of energy, because energy doesn't have any charge, if you form an electron out of energy, you also have to form an anti-electron, something with the opposite charge, so that you make the charges sort of stay conserved. Okay? So you can't start with something that's uncharged and end up with charged stuff. So basically for that reason, you have to have some anti-electrons around. And so we think everything in the universe formed from energy. And so we should have had equal amounts of stuff and anti-stuff in the universe. But, today, if you look in the universe using telescopes, using experiments, whatever it is, there is no natural antimatter anywhere. Now, we can make antimatter in the lab artificially, and we've studied its properties. And that's the other bizarre thing. We've studied its properties, and it seems to have exactly the same properties as regular stuff. You take an anti-electron, exact same mass as an electron, exact same spin as an electron. The only thing that's different is its charge. And the same for, even anti-atoms, anti-hydrogen, and so on. So the mystery is when matter and antimatter have exactly the same properties, and when we think they should have been made in equal amounts after the Big Bang, why do we only have matter left? What happened to all of the remaining antimatter? That's a crazy question.
You should
that's
ask
the
the universe, what's the matter with you?
That's a good one.
So what happens if, only you wouldn't like that joke, but anyway. Is it, supposedly I've heard again, you bring matter and antimatter together, they annihilate each other.
Right.
Is that true? And has anyone in a lab, created a vacuum where you could have a matter and an antimatter electron and watch them collide?
Yeah.
And what happens?
That stuff happens. That's a thing we can do routinely. And yes, they do annihilate and they give off light. They turn into photons. So you take an electron and an anti-electron and you let them touch each other. They both go away and then you're left with photons. So
they give off light, like visible light, or just some wavelength of light.
So energy has to be conserved, right? And what that means is that if you take an electron and an anti-electron and you add up their masses and then multiply that by c squared, with the speed of light squared, that's how much energy there is in these. And so if they have to sort of move away, then what has to be left behind is energy equal to their original masses times the speed of light squared. And so that energy for electrons turns out to be at sort of a gamma ray wavelength. So it's not visible light. It's not something you could see with the naked eye, but it's a gamma ray photon. And when it goes and hits a piece of metal, for example, it's easy to detect and it clicks. And so that's a fairly standard thing. And people have, of course, also seen that other weird kinds of antimatter also annihilate. Antiprotons annihilate, anti-atoms annihilate.
So is there, you could associate a spectra, so you could look for matter-antimatter collisions all throughout the universe, right? If you knew the spectrum.
Exactly. And in fact, that's one of the ways in which we know that there's not really that much antimatter in the universe. So let's say there was some distant galaxy that had tons and tons of antimatter. If there was any matter nearby, and if those two interacted, you would see very, very, very specific wavelengths of gamma rays come off from those regions. And so that's the sort of argument by which we know that, there must not be any big boundary between the matter, at least as far as we can see, we can't see the boundary between the matter-dominated part of the universe and the antimatter-dominated part of the universe. Because, one theory could be, maybe it just got segregated, right? Maybe all the antimatters are hiding out in some different part of the universe, and we haven't, some other matter all got to end up in our part of the galaxy or our part of the universe. But that argument also doesn't seem to be quite right, because if it was, we would see lots of these very specific gamma rays coming off from the boundary zone.
Are there objects that can only be created by the energy released from matter-antimatter interactions? The nature of the photons released, are they able to create things that otherwise could not be created because that particular electron, that particular energy, photon just isn't around except from those kind of collisions?
That amount of energy it's a huge amount of energy, right? Like it's enough energy to blow apart pretty much any other stable atom or molecule. And so the energy from annihilation of electrons and anti-electrons, the protons and antiprotons, tends to be very, very high energy photons. And so these things are usually more destructive than creative. But we can, as I said, we can see them sometimes. So here's a weird thing. So it turns out every time there's a big thunderstorm, there's actually lots of anti-electrons formed due to the energies in the thunderstorm. And that always blows my mind. It's something that people learned fairly recently. But yeah, so you can make antimatter, and you can see examples of it even above clouds.
How do you make antimatter?
The opposite way, right? So, for example, in the labs, when we make antimatter, the way we do it is basically by dumping a lot of energy into a small region. And so if you think about things like the Large Hadron Collider, one of the things they do is they smash a bunch of particles and make a lot of energy from the collision of these particles within a small volume. And that energy, there's so much energy there that it turns into new kinds of particles. And so, you've heard of things like the Higgs boson being created at the Large Hadron Collider, but of course they also make lots and lots of other kinds of antiparticles and exotic particles.
So when lightning strikes, how are anti-electrons created there? What's doing it?
So I honestly don't know much about the exact mechanism, but I imagine it must be because there's so much stored energy in these lightning discharges. But the exact mechanism, I don't know. I suspect it's a complicated enough mechanism that not many people know about it either.
Okay. Well, any thoughts about the near-term future? Are there any of these big questions that we're even getting closer to answering? Or, what's your sense of the progress of this physics over the next few years? Or, who knows? It's anyone's game. Or do you sense any big breakthroughs coming? We're going to observe them.
Well, so a lot of people are looking, right? And it's becoming more and more people are getting interested in this question. There are lots of smart people thinking very hard about these kinds of questions. And so I suspect that I hope it's not really, I don't really have any basis for this, right? Other than just sheer optimism. But I hope, and I think it may not be too unrealistic a hope based on how people are doing things, that in maybe the next decade, we'll actually learn something about dark matter, at least. Because there's such a huge variety of experiments looking in lots of different ways that we've got to be able to find it soon. Otherwise, it's going to be embarrassing. Dark energy, though, I don't know. Dark energy is a really weird one. It's crazy enough that we honestly don't even have any really trustworthy theoretical guidelines to help us figure out how to look for it. It's really.
Well, is there anything that could explain, the movement of galaxies, et cetera, except dark matter and dark energy, or that's the best we have?
That's the best we have. As far as we know, those are the only things. But even questions like, is there only one kind of dark energy, or are there different kinds of dark energy? Well, we don't know. And what's causing all that? So yeah, we really don't know anything about these things other than that they sort of behave like energy and they're making galaxies blow apart. And then the third one, this question of why there's more matter compared to antimatter. Again, that's a thing where I know that there are lots of smart people kind of looking in lots of very different ways. Some of these ways involve using atoms and molecules and making really precise measurements on them. And there, again, I don't know. I feel like of these three questions, the dark matter question is the one where we're probably going to find the answer soonest. But ask me in a decade, or ask whoever finds it in a decade, I guess.
Okay. Well, very good. What's the best way for people to find out more about your work and to to get in touch or at least see what you're working on?
If they're interested in my specific work, I'm always happy to chat. If you just shoot me an email and go to my website, then yeah, just feel free to get in touch with me. I won't promise I'll answer every question, but if you ask me an interesting question, I'll try and give you an interesting answer. Other than that, if you're generally more interested in what physicists are up to, there's a really good online publication by the American Physical Society. It's just called Physics. So if you go to the American Physical Society's webpage, you'll be able to find it. And it's really a neat way to keep in touch with all of the latest developments, lots of different fields. but including some of these kinds of questions that I talked about today.
Well, very good. Well, Amar, thanks for coming, and I appreciate you.
Thanks for having me, and
revealing
thanks for all the great
the
questions.
mysteries of the universe. Yeah, no problem.
We can but try. We don't know what we're going to find, but it would be silly not to at least try. We're trying.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.